Hello, in this video, we're going to talk about link systems. So in biomechanics, we use the term link a lot. We're just meaning segment or piece of the body, essentially. So when we link together a whole bunch of links or segments, we can make a link system. So the body is one large link system made of rigid or semi-rigid bodies that form a kinetic chain. Okay, so a link system is essentially a kinetic chain. It's the whole series of links that are connected. Forces are applied to links to cause motion. So that'd be like muscle forces or gravity or all sorts of different forces. In the body, bones are levers that rotate around joints, and joints serve as the fulcrums or axis. All right, so the mass of each link is less because bones are not completely solid. Okay, so we want less mass essentially for efficiency of movement. Less mass in the limbs means we have to produce less muscle force to move the limb. Okay, so thankfully, bones are not completely solid. We've got that space in the middle, and we've got some spongy bone. So bones are not completely solid, which means they're of less mass, which means there's less resistance for the muscles to have to work against to cause movement. Bone and muscle mass increase in response to weight-bearing activities. Okay, and we've talked about this in past videos, and I'm sure you've covered this in other classes. But bone and muscle mass, when we engage in weight bearing activities, which can be all kinds of different things, strength training, um, running, anything that is working against gravity, we'd count that as weight bearing. So bone and muscle mass increase in response to weight bearing activities, and bone and muscle mass will decrease or atrophy due to disuse. Because in that case, then the weight of our limb or the mass of our limb is going to stay like if it didn't atrophy, the weight of the limb would stay the same, and the strength of the muscle it has to move that limb will be decreasing due to disuse. And so it's important that it all decrease proportionately so that we don't lose the ability to move. Because if at some point the limb is heavier than what the muscles can move because that limb didn't atrophy significantly or atrophy sufficiently, I should say, then we would lose the ability to move. Okay, so everything atrophies proportionately due to disuse, and in a biomechanics, from a biomechanics view, that's a good thing because otherwise the weakening muscle wouldn't be able to move the body. The body might cause atrophy of muscles in response to increasing the weight of a segment. Okay, so this is something you may not have thought about before. If we increase the weight of a segment, like let's say, for example, the arm is in a cast. Okay, so that's a way where we increase the weight of the segment by adding a cast to the arm. Okay, so, and this is irrespective of whatever the injury was. So I'm not saying that, like, let's assume that the muscles, bones, everything that are part of that limb are intact and healthy. Okay, now if we add to that a cast, we've added additional mass or additional weight to that arm. So, of course, when we're in a cast, we know that we're going to have some amount of atrophy due to the disuse of the muscles in that cast. But the amount of atrophy is disproportionate to the amount of disuse. So, like, let's say I have my two arms and I don't use them at all. I equally disuse my arms, but one is in a cast and the other I'm just choosing not to use. They will have an unequal amount of atrophy, even though the amount of disuse is equal. Okay, the reason they'll have an unequal amount of atrophy is because of the added mass of the cast itself. So to adapt to the increased weight of the limb, so to the extra mass added by the cast, the muscles atrophy to decrease the mass of the limb to improve the movement. Okay, so the limb, to make up for the extra mass of the cast, will actually atrophy to reduce the mass of the limb so that we don't have as much of an issue in our normal movement. So it's sort of like the muscle is decreasing to try and make up for the fact that the limb increased when we added the cast. So it's a disproportionate loss of muscle and bone mass compared to the amount of actual disuse that's caused. The mass of a limb is distributed to maximize ease of movement and minimize resistance to that movement. Okay, so if we want to increase our mechanical advantage of the muscle, a key way that the body does that is by moving the center of mass of that limb more proximally. The more proximal the center of mass is, the shorter the resistance arm is, and the less force that muscles have to produce to be able to move that limb. So muscles that move a link are primarily located on the link that's proximal to it. So that's not an absolute rule. That's not always true, but for the most part, like our muscles that move the glenohumeral joint are going to be on the chest and back. The muscles that move the elbow are in the upper arm. The muscles that move the wrist are in the forearm. So again, that's not absolute. That's not always true. We can come up with exceptions, but for the most part, that's usually how it works. And what that does is that makes it so that the whole limb tapers so that the concentration of mass is more proximal in each segment and of the whole limb. So muscles cross the articulation between the two links and insert proximally on the moving link. So we're keeping more mass, the muscle mass, on the proximal part of the limb instead of more distally. The mass of each link is progressively less the more distal the link is from the trunk. Okay, so what we're saying is the hand is smaller than the forearm, which is smaller than the upper arm, which is smaller than the chest. So the further we get from the trunk, the smaller the segment. The mass of the entire limb tapers from proximal to distal because it gets smaller and smaller. And the mass of each link individually tapers as we go from proximal to distal. So just looking at this picture, you know, we're tapering from a larger shoulder down to a smaller elbow. And then at the elbow end of the forearm, it's larger and it tapers smaller as we get closer to the wrist. So each link tapers. And what that does is it forces the center of mass more proximally of both the whole limb and of each individual segment. Okay, the mass of the limb is located closer to each axis of rotation. So the closer the resistance is to the axis of rotation, the shorter is the resistance arm. So it's possible that that's why it's harder to build more muscle mass in our distal segments of our limbs. So you may have had this issue yourself or heard bodybuilders or different types of athletes complain about how they're having a hard time causing hypertrophy or building new muscle mass in their calves or their forearms. It's a really common problem. That's a common complaint. Arnold Schwarzenegger had that complaint. He had a hard time building mass in his calves. And it's possible that it's because the body is reluctant to increase the mass at the distal segments because that is going to interfere or could potentially interfere with our normal free movement. That's especially true if we are trying to hypertrophy the distal segments disproportionately to the hypertrophy we're achieving at more proximal segments, because we always want the center of mass to be more proximal. So we're not going to be able to hypertrophy our distal segments disproportionately to our proximal segments because that would shift our center of mass too far distally. So I would say that if we're trying, like, let's say we're trying to build more mass in the calves, we have to make sure we're doing enough thigh and glute work to be able to achieve that. So even if we're doing everything right for the calves, if we're ignoring the more proximal segments, the body is going to be reluctant to add that extra mass because we won't have the additional muscle mass more proximally to keep the center of mass more proximal. Okay, that is all I have for you on this one, and I'll see you next time.